Ozonolysis is a way of cleaving alkenes. Now, it's a two-step procedure consisting of ozone as the first step, followed by a workup step. And the workup step can be oxidative or reductive. The difference between the two is in the reductive workup, aldehydes can survive. In the oxidative workup, you cannot have an aldehyde present. All aldehydes are converted to carboxylic acids. So, it's actually quite easy to predict the products of an ozone reaction. You basically find your alkene, in this case we have cyclohexene, and you break the carbon-carbon double bond. And on the carbons that were part of that alkene, the sp2 carbons, they end up being double bonded to oxygen. So here we have 1, 2, 3, 4, 5, 6. So chain of 6, and we see that right here. Carbon 1, 2, 3, 4, 5, 6. 6 is attached to a hydrogen in carbon 5, just like over here. Carbon 1 is attached to a methyl group in carbon 2, just like over here. This is the product. In the case of acyclic alkenes, you actually break the molecule in half, like so. As a result, this is the left half, this comes from the right half. The mechanism of this can be quite complex. Whether the oxidative workup or the reductive workup, the first part, the ozonolysis, is the same, in which you have ozone, like this, takes part in what's called a 3+2 cycloaddition, where these three atoms add to these two atoms. Here, the O- sends its electrons to one of the alkene carbons. The carbon-carbon double bond leaps up to this oxygen, and the pi electrons from the oxygen-oxygen double bond go on to the central oxygen. And in this irreversible process, you end up with this molecule, like so. And this is what's referred to as the primary ozonide. Now, the primary ozonide is not too stable because it has two oxygen-oxygen bonds. And as a result, this molecule breaks apart. The carbon-carbon bond here is broken to form a carbon-oxygen bond, carbon-oxygen double bond, and that sends these electrons onto the central oxygen. There's the driving force for this reaction, is the breaking of this oxygen-oxygen bond. And then a lone pair from this oxygen comes down and completes the cycle. You end up getting this molecule from the left half and this molecule from the right half. Now I drew it upside down because the next step, these two molecules rapidly recombine. O- goes to this carbon. The electrons from the carbon-oxygen pi bond go to this carbon, and these electrons from the carbon-oxygen pi bond go onto the positive oxygen. And as a result, you get a mixture of diastereomers of this. And this molecule right here is referred to as the secondary ozonide. And this secondary ozonide waits until the workup step, whether oxidative workup or reductive workup. In the reductive workup case, you add either triphenylphosphine or dimethyl sulfide, either one. Well, let's just add triphenylphosphine. And you can have that attack from either side, And with sulfur and oxygens, they have a tendency to bond really strongly with oxygen. They like attacking oxygens, especially oxygen-oxygen bonds. So in a very similar reaction to an SN2 reaction, the phosphorus attacks the oxygen and kicks this oxygen off. The result is you get this O- here, oxygen, here. And this O- can come down and create a carbonyl by kicking this oxygen off. Carbonyl formation is typically a very favorable reaction. And you form one of the two products. Plus this O- here, positive oxygen there. And then these electrons from this O- come down to reform the other carbonyl. These electrons kick off the triphenylphosphine oxide. You get your other product plus triphenylphosphine oxide, which is actually quite stable compound. It's sometimes referred to as, well, brick dust, because it really doesn't do anything useful. It just sits there. So, and we get the two products from the ozonolysis reaction.